Hey everyone, today we're going to talk about a high frequency, high voltage amplifier. It was originally designed for testing wire insulation, but I found out after I started prototyping stuff, it wasn't really going to get me to the voltage levels I needed. This one will only output around 1 kilovolt peak to peak, and to test like magnetic wire insulation well, I really need something closer to like 3 to 5 kilovolt peak to peak to cause kind of a measurable breakdown that's repeatable. But I thought it turned out pretty cool anyways, so I figured I'd make a video about it. I also did a really decent write-up on Hackaday if you're interested in more of the nitty-gritty technical details. Check it out in the link in the description below. So jumping into it, first I kind of went through 2 revisions. So the first revision, pretty straightforward. My Fluke high voltage power supply is driving it. That became limiting because it only has about 30 milliamp output. And the transistors that are used in it are silicon JFET. They're really nice, but they're designed for higher power handling, and the package parasitics are not ideal for this application. So I ended up swapping those out in Rev 2 for just a standard depletion mode MOSFET. The other difference you will see between this first revision and the second one is the transformer. This one's using a U-core transformer. They're usually used for high voltage applications, like they're the design that's used on flybacks for CRT televisions. They have worse inductive parasitics. I wasn't overly concerned moving into this project with how the transformer parasitics were going to end up. I figured it was much easier just to build a prototype and see what it looked like, and then maybe try and simulate it further, which you'll see towards the end of the video. I do have a pretty decent transformer simulation. But I ended up moving on and going with a high performance toroid transformer with some nanocrystalline ferrite structure made by a German company that I'm not going to try and pronounce. But its characteristics are really phenomenal. I would suggest you look into it if you're into magnetics or inductors at all. But let's take a look at how I made that U-core transformer here. That looks just like this. I made a cut video of me just winding the bobbins and coils and putting it together, and hopefully you find that interesting, and then stick around for Rev 2 and the rest of the video about some lab results, the 3dB frequency points, simulations, etc. U-core transformer. Typically they're great for high voltage because you can isolate the primary from the secondary, but you can't always find commercially available bobbins. So the easiest solution I have for this is just a simple Kapton strip. They're popular for like 3D printer beds. And then find a dowel approximately the same size as your transformer core, and we're just going to wind that Kapton strip around the dowel to make a relatively firm bobbin, to in turn wind our wire on. Obviously check if it fits first. Then I'm just going to tape it to that bobbin with some electrical tape to hold it in place. At which point, using Kapton tape, I'm going to stick one of the wire sides onto my bobbin there. And now for this process, I was using 40 gauge wire, which actually broke twice while I was trying to wind it. So you'll find out the winding on here looks a little messy, and that's because I was more focused with just getting a working prototype and not snapping that hair thin wire. Actually, I think it's thinner than hair, to be honest. So I would recommend you stop every 5-10 turns and push the wire over to make sure it looks nice and that your windings are all uniformly distributed. In this case, I didn't do a good job of that. Now, because this is going to be a high voltage transformer and also to protect those windings, typically I'm just going to put a layer of Kapton tape over it. So that's what I'm doing here. I have a few different rolls of width, and I just find one that's close and again wind it with the drill. And once this process is complete, here you'll have a beautiful looking prototype core that then I'll electrical tape together. Here we have the second revision of the whole amplifier. I replaced the lab power supply with a 1-to-1 isolation transformer, so it can take 120 in and output 120 or 240. So with this switch I can toggle between 180 and 340 volt DC bus. On the input, I just have a simple half-amp circuit breaker. Coming off the transformer, this is just a collaged together AC to DC rectifier with 2 random capacitors. Ideally, you'd put a light on here to have more of a safety indication that this is on. Right now there is none, so it's really easy to forget about that. We have a new transformer. As you probably can see, it's not the U-channel one, it's a high-performance toroid. Then we have the more finalized amplifier itself. So zooming into the board here so we can see it in a little more detail, we have some additions and changes from the first version. We added this pot to set the bias better, which is currently at about 50 milliamps. And we have different transistors. These are actually the same model. They're depletion mode MOSFETs, so DN2540s. And the reason I changed to those is they have a lower input capacitance and lower parasitic like gate to drain capacitance, so their Miller capacitance is better. Basically, in general, they're better for the high frequency performance that I'm looking for. So let's take a look at the 2 transistor design I have here. It's a Cascode, and the way that works, or the benefits of it, is easier to point out when we look at a schematic. Alright, so looking at this Cascode transistor pair, there's a few things that make it really convenient to use for this type of application. First, the current running through this transistor set is completely set by a bias resistor here. And the way that works is this transistor turns on as long as the source is about 1.5 volts above the gate. So by connecting the gate to ground, as current flows, the source lifts in voltage due to this resistor until you get to a steady state current. So in the case of my circuit, it's adjustable, but somewhere around 50-60 milliamps is about the maximum thermal dissipation for the transistors. Now, why do we have 2 transistors set up like this? Well, what kills high frequency performance is input capacitance, which is really a huge factor of Miller capacitance. And what that is as your voltage changes between the top of this transistor and your gate, there's essentially a huge capacitor that you're charging and discharging. And that capacitor is actually related to the gain. It's proportional to the gain of the transistor. So higher gain, more Miller capacitance, it destroys high frequency performance of a single transistor amplifier. The way you get around that with a Cascode is you never change this voltage right here. So in the case of my circuit, I believe it's set around 12 volts. And the way we set that is, again, since it's only a 1.5 volt difference, we just do a voltage divider with two resistors. Set this point at about 10.5 volts. Lo and behold, this always holds 12. But the current is amplified through this same transistor. So when the current varies here, the same amount of current varies here without the voltage changing. And since we have our load between the high voltage and the top of this transistor, we have that large current variation that we're generating with this small transistor here, which also equates to a relatively large high voltage swing. So that is the magic of a Cascode amplifier and why they're really popular in applications like this. Okay, here's the simulation model. We have a 180 volt bus. We have our input here, which is capacitively coupled. That goes into our first transistor. That's the TO92 package. This resistor sets our bias. And then we have the upper transistor here that's handling most of the high voltage. So you can see here's our resistive divider to set the voltage set point that keeps that Miller capacitance at bay, and the real secret to that Cascode. This is the feedback network C4R7. It's just an RC feedback network from the primary side. You would ideally get better performance if you took the feedback from the secondary side, because it would also cancel out any losses due to your transformer. In my case, the transformer is not that lossy, and experimenting with different transformers, I didn't want to deal with stability issues that would potentially creep up as a result of that. So I said, good enough, just wrap the primary side. This complex looking model up here is that transformer. I was modeling, obviously I have the real magnetizing inductances, L1, L2. L4 and L3 are the leakage inductances. And then I had some parasitic capacitances modeled as well. This was as I was experimenting with the U-core versus the toroid. I was trying to model something that was actually correct for the high frequency losses, and I got pretty close, as I'll show you in a second. Finally, the output is just into 500k ohm load. This was designed for high impedance loads, although it actually will drive downwards to like 50k ohm without too much of a problem, as long as it's not a capacitive loaded load. So this 7 picofarads is actually modeling my oscilloscope after I found out that that's what was really killing the high frequency, not the transformer. So if we simulate this guy here, you can see the output is not terribly different looking. This is from 20 kilohertz to 1 megahertz. So looking at the simulation here, the cutoff for 3dB is approximately around that 20 kilohertz that we show in the lab, and that's really driven by the transformer. If I increase the primary inductance, this would go up. The high frequency side falls off around a megahertz here, and that's highly dependent on the lab setup, the wiring, etc. So I call it good enough for this model. Looking at the DC operating points here, we can see this midpoint is approximately 12 volts, and it varies just a tiny bit. So instead of a full voltage swing of 100 volts here, you have millivolt level variation, which ensures that Miller capacitance is very low to non-existent. Our bias in this case is on average around 60 milliamps in this model, so it's swinging 70-45. And our output, now this is at 200 kilohertz, we're just swinging plus or minus 150 volts. So that's it for the modeling. The one thing I did learn, I thought a lot of my parasitic problems were from the transformer and the transistors. As it turns out, I grossly underestimated how much capacitance from something even as simple as a scope probe can affect my output. So here I just have a 100-to-1 scope probe that has 6 picofarads of capacitance, which typically I would ignore. I don't even really think about that in most of my lab measurements. Especially at low voltage, that's not a huge problem. But what I failed to anticipate was the amount of energy required to charge and discharge that capacitor at high voltage and high frequency like a megahertz. So that 6 picofarads at 1 megahertz equates to 27 kilo ohms roughly of impedance. Again, normally wouldn't be a problem. As it turns out though, with a 500 volt swing, which is the minimum goal for this amplifier, that means I'm sinking 18 milliamps at the peak of that sine wave into the capacitance of the scope probe alone, which when I consider I only have a 50 milliamp bias going through this entire channel, that's already taking a considerably large fraction of the power that this amplifier can output. So I'm at the point that I can't really improve the output performance of this much more. It's not about limiting parasitics. It's literally because I don't really have a matched load like what you would have with an RF type system. And being a Class A analog amplifier, although with this it's not quite Class A, because you have that inductive voltage doubling. But regardless, the efficiency is quite low, somewhere around, I believe, 30, 40, 50% is the max efficiency you're going to get out of this. To make this a better design, I would want to move away from a Class A style design and instead go to like a push-pull transformer with a high step-up ratio and a tuned resonant filter on the output, or actually make it a tuned resonant transformer. Then I'm just hard switching transistors, so the losses are very low, especially with something like a gallium nitride or silicon carbide. And I'm still going to get a sinusoidal voltage output due to that resonance point, as well as an additional voltage gain. Okay, so looking at the setup here, I have my 100-to-1 oscilloscope just acting as the load on the output of the transformer. I also have the second scope channel measuring the voltage on the source of this FET. So really across our bias. So as that voltage goes up, that means the bias current is going up, and when it bottoms out, then we're have no more bias current flowing. Obviously, input signal from my signal generator that right now is sweeping 20 to 1.5 megahertz, so 20 kilohertz. And the sweep time is set to be the full length of the oscilloscope trigger. So I already plotted it out with the cursors here. But essentially our 3 dB point, so from the peak down, is 20 kilohertz to approximately 1.2 megahertz. And you can really quickly tell what's causing that, because I have a feedback, negative feedback on this circuit. If you look at the purple trace here, you can see at the lower frequency, 100, 200 kilohertz, our bias current is not changing very much. In fact, let's zoom in. So this bottom, the ground for it is right here. So our bias current isn't varying very much, and it's well above ground. As we move this way, the bias current increases from the negative feedback. It is trying as hard as it possibly can to keep that output signal at the same gain, till eventually we hit a point where that bias current starts bottoming out. So it actually goes to 0 milliamps, which puts the transistors into cutoff. Now, the performance as we just start to touch cutoff isn't horrible, and that's really being driven because we have an inductor in the circuit. It helps carry some signal through even when the transistors technically aren't conducting anymore. But towards the 3 dB point here, we're getting into hard cutoff, and that amplifier just cannot put any more power out. So one way to increase this frequency response would be to just continue to dial the bias current higher, which is going to be efficiency loss, and it's going to be higher thermal dissipation, which we'll pop a picture of the thermal scan of this shortly, but we're already maxing out the thermal capability of these packages roughly. So there's not a lot of headroom left there. And it would just be a poor design to continue to increase that. We'd really, like I said earlier, need to move to a different architecture, like a resonant push-pull transformer that's operating in like a Class D amplifier instead of a linear amplifier like this. But I still am really surprised by just this really not ideal layout and 2 cheap transistors and a high quality ferrite. The span of gain I really can. Right now we have a 250 volt peak to peak output, and we can crank that up just by varying the signal generator here. We can see what our max output is pretty easily. Zooming in on the oscilloscope here, we can look at the most optimal performance, which is centered around 150 kilohertz approximately. And if I turn this guy on, we can see 2 things. First of all, our sine wave is no longer very sinusoidal. You can definitely see some distortion. And this purple, our bias current, which I can actually adjust here with our, so that's lowering the bias current. We can see the transistor goes into cutoff a lot sooner. And normally this would be chopped harder, but you still have some rounding here due to the inductance from that transformer. So if we maximize the bias all the way up, we can hit a peak of almost 1,000 volt peak to peak output. So we're at about 970 right now. So if we bump the bias up even a little bit more, we'd be able to see that. Unfortunately, like I said earlier though, looking at the thermal images, we're already getting pretty hot, as well as calculating the power dissipation here. It is not negligible. So again, not ideal for testing insulation. The voltage just isn't quite high enough, and it becomes too lossy, or there's too much, I don't want to say parasitics, but the loading of even just an oscilloscope to monitor the output voltage becomes a problem. So for the actual implementation of a insulation tester, I'll probably be making a video in the future with a half bridge or full bridge resonant transformer instead. Hopefully you guys found this interesting. Thanks for watching, everybody, and we'll catch you next time.